There's a star in the night sky that has been dying for millions of years, and we have been watching it without fully understanding what we were seeing. It sits at the left shoulder of Orion, visible to the naked eye from anywhere on Earth with clear skies, and it has been one of the most studied stars in the history of astronomy. Its name is Betelgeuse, and right now in 2025 and 2026, a series of discoveries made with the most advanced space telescope ever built, combined with a confirmed detection that settled a century-old argument, have sent astronomers into a genuine scientific debate about when the star is going to explode, what kind of explosion it will produce, and whether everything we thought we knew about its behavior was being misread the entire time. This is not hype. This is what is actually happening in astrophysics right now, explained properly. To understand what James Webb has revealed about Betelgeuse and why it matters so much, you first need to understand what kind of object Betelgeuse actually is and why it occupies such a unique position in astronomy. Betelgeuse is a red supergiant, one of the largest and most luminous types of stars that exist. It sits somewhere between 550 and 700 light years from Earth, depending on which measurement method you trust, and its exact distance has been a source of genuine scientific disagreement for decades. What is not in dispute is its scale. Betelgeuse is approximately 700 times larger than our Sun. If you placed it at the center of our solar system, its surface would extend past the orbit of Jupiter. It burns at roughly 100,000 times the Sun's luminosity. It has already exhausted its hydrogen fuel, moved through helium burning, and is now fusing heavier elements in a core that reaches temperatures of 100 million degrees. Every measurement points to the same conclusion. This star is in the late stages of its life. The question that has driven astronomers for generations is not whether Betelgeuse will explode. The question is when. Like or subscribe, because the answer just got a lot more complicated. To understand the modern debate, you have to start with the event that triggered global headlines in late 2019 and early 2020. Betelgeuse dimmed, not slightly, dramatically. Between October 2019 and March 2020, the star faded to approximately 40% of its usual brightness, becoming noticeably dimmer to the naked eye in a way that stunned casual observers and professional astronomers alike. This event, which became known as the Great Dimming, set off immediate speculation that Betelgeuse was entering its final phase and that a supernova could be imminent. Media coverage was intense. The word imminent appeared in hundreds of headlines. Astronomers themselves were genuinely uncertain about what was happening, because nothing quite like it had been observed before at this scale. What James Webb and subsequent analysis eventually helped establish is that the Great Dimming was not a sign of imminent stellar death. It was caused by something far more physically interesting and far more revealing. A massive convective eruption in Betelgeuse's outer layers had ejected an enormous plume of hot gas from the star's surface. So large, it made the event known as the surface mass ejection, a stellar version of what our own sun does in smaller solar eruptions, but on a scale without parallel in documented stellar observation. That ejected gas cooled rapidly as it moved away from the star's surface, condensed into a cloud of solid dust particles, and that dust cloud drifted between Betelgeuse and Earth, blocking our view and making the star appear dimmer. It was not the star itself fading. It was a dust veil we had briefly pulled between ourselves and it. Like or subscribe, because the James Webb data that came after changed the interpretation of that event again, and in a way nobody anticipated. The James Webb Space Telescope, with its extraordinary infrared sensitivity, has been able to observe Betelgeuse's outer atmosphere and stellar wind environment with a precision no previous instrument could match. Infrared observation is critical for studying Betelgeuse because the dust and gas clouds surrounding the star, which block or distort visible light, are essentially transparent to infrared wavelengths. Webb sees through the veil. What it has observed in its monitoring of Betelgeuse includes highly unusual and asymmetric dust structures surrounding the star, dense, uneven clouds that indicate the 2019 surface mass ejection was not a singular hiccup, but possibly the most dramatic outburst from this star in recorded observation. Webb's infrared spectroscopy has tracked abnormal behavior in Betelgeuse's outer layers, including what researchers have described as extreme convective pulses, giant cells of boiling hot plasma rising and falling beneath the surface in patterns consistent with a star undergoing significant internal instability. The convective cells on Betelgeuse are so large that a single one of them would be larger than the entire distance between the Earth and the Sun. What Webb's data also shows, and what has been the subject of the most intense scientific debate, concerns the stage of nuclear burning Betelgeuse is currently in. The most alarming interpretation of the available evidence has been advanced by researchers who argue that Betelgeuse may have already moved past helium burning into carbon burning, the second to last stage of a massive star's life before gravitational collapse. A 2023 paper published on the Archive Research Repository, analyzing Betelgeuse's pulsation periods, argued that the star's behavior is consistent with a star in the carbon-burning phase, which would suggest a supernova not in tens of thousands of years, but potentially in tens of years. That is a statement so extraordinary that it deserves to be said slowly. Some researchers believe Betelgeuse could be within decades of exploding, not centuries. This interpretation remains contested. Other models place Betelgeuse firmly in the helium-burning phase, with hundreds of thousands of years remaining. The disagreement is not about sloppy science on either side. It is about the genuine difficulty of looking inside a star from 640 light-years away and inferring what is burning in its core from nothing but the light it emits and the way its surface moves. Like or subscribe. Because the discovery that changed this entire debate the most was confirmed not by Webb, but by a telescope in Hawaii on a single night in July 2025. For over a century, astronomers had suspected that Betelgeuse was not alone. Radial velocity measurements going back decades, astrometric data, and the star's known rotation rate, which appears too fast for a single aging star of this size, all pointed toward the existence of an unseen companion. Various theories had been proposed. Hubble tried to find it. The Chandra X-ray Observatory looked for it. For decades, nothing conclusive emerged. Then on July 21st, 2025, a team led by Steve Howell at NASA's Ames Research Center announced what the astronomical community had been waiting for. Using an instrument called ALAPEC on the Gemini North Telescope in Hawaii, a device designed specifically to perform speckle imaging, a technique that overcomes atmospheric distortion by taking thousands of extremely short exposures and combining them, the team detected a companion star orbiting Betelgeuse for the first time in history. The companion was confirmed. It was given the name Siwarha, from the Arabic meaning her bracelet, echoing the Arabic roots of Betelgeuse's own name. Siwarha is a hot, blue-white main sequence star with a mass estimated at 1.4 to 1.6 times the mass of our Sun. It is approximately 6 magnitudes fainter than Betelgeuse, meaning Betelgeuse outshines it by a factor of roughly 250, which is why it went undetected for so long, despite its relative closeness to the red supergiant. Its orbital period around Betelgeuse is approximately 2,100 days, which is roughly 6 years, and that 6-year orbital period immediately unlocked something that had been puzzling astronomers for a long time. Betelgeuse has 2 known brightness cycles, a primary one lasting around 400 days, and a longer secondary cycle lasting roughly 6 years. The 6-year brightness variation, known as the long secondary period, had never been fully explained. The confirmation of Siwarha, with a matching 2,100-day orbital period, strongly suggests that Betelgeuse's long-term brightness fluctuations, the ones that had been interpreted by some researchers as signs of deep internal instability, are not coming from inside the star at all. They are being caused by the gravitational influence of its companion. Like or subscribe, because this single discovery fundamentally changes how every observation of Betelgeuse from the past century has to be reevaluated. The implications of Siwarha's confirmation for the supernova timeline are significant and are currently being debated actively in the research community. On one side, the discovery of a companion that explains the 6-year brightness cycle removes one of the key pieces of evidence that had been cited in support of the more alarming timelines. If Betelgeuse's long-period variability is gravitational rather than a sign of late-stage nuclear burning, then models suggesting the star might be in its final decades become considerably less supported. Current mainstream astrophysical models, in light of the Siwarha confirmation, place Betelgeuse in a stable helium-burning phase, with the supernova most likely still within 100,000 years, a time frame that sounds long in human terms but is cosmically brief for a star. On the other side, the existence of a close companion introduces a different kind of complexity. Morgan McLeod, an astrophysicist at Harvard, has suggested that Siwarha orbits so close to Betelgeuse that the 2 stars may actually merge before Betelgeuse goes supernova. If that merger happens, it would splash out gas, dramatically spin up Betelgeuse's rotation, and potentially alter the properties of the eventual explosion in ways that existing supernova models have not accounted for. We think the stars might merge even before Betelgeuse goes supernova, McLeod said. This would potentially affect the properties of the eventual supernova. That is not a minor footnote. That is the difference between a well-understood Type 2 supernova and something that may not fit neatly into any existing category. The role of James Webb in all of this is not to provide a single definitive answer. It is to provide the data quality that finally allows these questions to be asked with precision. Before Webb, studying the outer atmosphere of Betelgeuse in the infrared was limited by the sensitivity and resolution of ground-based instruments. Webb's ability to observe in mid, Infrared wavelengths with space-based clarity means it can track dust formation in real time around Betelgeuse, map the asymmetric structures in the stellar wind with a detail never previously possible, and detect the spectroscopic signatures of what is happening in the star's outer layers across a full infrared spectrum. In June 2025, Webb also became the first telescope to directly identify the progenitor star of a different red supergiant supernova, a star in the galaxy NGC 1637 that exploded and was cataloged as SN 225. What Webb found was that this star had been hiding behind thick dust, appearing 100 times dimmer in visible light than it actually was. That discovery solved a long-standing mystery in stellar physics about why massive red supergiant stars seem to rarely appear as supernova progenitors. The answer is that they are there, but hidden by their own dust. This directly informs how astronomers interpret Betelgeuse's dust-shrouded outer layers and what those structures might be telling us about the star's current state. There is one more layer to this story that rarely gets explained in mainstream coverage, and it concerns what a Betelgeuse supernova will actually mean scientifically beyond the visual spectacle. When a massive star-like disappears, the outer layers of the star are blasted outward at a significant fraction of the speed of light, seeding the surrounding interstellar medium with the heavy elements that were forged in its core over millions of years: carbon, oxygen, silicon, iron, and elements heavier than iron that can only be created in the extreme conditions of a collapsing stellar core. The iron in your blood, the calcium in your bones, the oxygen in every breath you take, these elements were produced inside stars that exploded before our solar system formed and scattered their contents across the galaxy. Betelgeuse's supernova will add to that inventory. The material it ejects will eventually mix with gas clouds in the Milky Way, and billions of years from now, may become part of new solar systems, new planets, and possibly new forms of life that we cannot imagine. The reason astronomers are so intensely interested in Betelgeuse's final fate is not just the spectacle of watching a star die, it is that every detail of how it dies, what nuclear burning stage it is in, whether it merges with Sawarha first, how its dust envelope shapes, the outgoing shockwave, will produce a different chemical signature in what it leaves behind. Understanding Betelgeuse's death is understanding the mechanism by which the universe manufactures the raw materials of complexity. That is what James Webb is helping to decode. And that is why the debate among astronomers is not just about one star in Orion. It is about the process that made everything. Where does all of this leave the debate about Betelgeuse's final fate? The honest answer is that the debate is more nuanced now than it has ever been, but also more grounded in actual data than at any point in history. The Great Dimming of 2019 is now understood as a surface mass ejection, not a supernova warning signal. The 6-year brightness cycle is likely explained by Sawarha's gravitational influence, not deep internal instability. Mainstream models currently place the supernova within 100,000 years, though some researchers argue the pulsation data supports a much shorter timeline. The possibility of a stellar merger before the supernova introduces a wildcard that could change the nature of the explosion itself. And neutrino detectors on Earth, which can detect the burst of neutrinos that would precede a supernova by hours, are already being monitored for exactly this event. When Betelgeuse does finally explode, it will outshine the full moon. It will be visible in daylight for weeks or possibly months. It will be the closest supernova visible from Earth in the modern era of telescopic astronomy, and every instrument humanity has built will be pointed at it. Like or subscribe, because the universe is running on its own schedule, and every observation we make brings us one step closer to understanding the most spectacular event the human species will ever witness in the night sky above Orion.